Yeah, so first, it's a great honor for me to speak in front of you. Today, I would want to share with you some recent results about the number counts in multiple ALMA bands. So the survey, the center just shared with us the very exciting result from the Rebels large program. Here I bring you with another survey, which is called ALMACAL. That is a survey that's trying to make use of the ALMA calibration observations. So it's a survey that somehow I think it's relevant to maybe most of you here, because when you're looking into your ALMA data, you will always find there are several calibrators that have been observed along with your SAPS targets. So basically those calibrators have been used to calibrate the flux density, the band path, and the complex gain of the telescope. But if you make an image for those calibrators, in most cases, you will find a bright point source in the center. And that's kind of boring, but it may tell you something that's whether you have made the correct calibration processes. But here is, if we remove the central point source, there is a much more interesting world behind the calibration. So on the left, we have shown that we have found one dusty star forming galaxy and also a radio blob that besides the central calibrator. And on the right, it's more interesting, where we have found quite extended radio jets. So because more than 95% of those calibrators are blazars, so it's quite often to find those jets along with those calibrators. So you may be wondering how and why we could do the science with those calibration observations. And here I showed you the statistics about the recent catalog that we made based on the ALMACAL. Here I just want to emphasize the total on source time. Besides ALMA band 5 and 9 band 10, where we don't actually have so many projects that are using those bands. But for the rest, the total on source time for every one of them are actually qualified to be the ALMA large program. And this is the same if we're looking at the total effective area, which is the total sky coverage that we combined all those calibrator fields together. And in ALMACAL, the total effective area is actually a function of the flux density. It is mainly because some of those calibrators have been observed more frequently than the others. So the sensitivity will vary from field to field. And this is why you find the effective areas change with the flux density. But if we focus on the band 6, for example, because where we have the two most famous blind ALMA survey, the ASPECS large program, the deepest blind survey available at the moment, and also the GOODS ALMA, which cover the largest sky coverage. But if you compare them with ALMACAL, you will find that the total sky coverage of ALMACAL at the sub-Milijansky level are already larger, even larger than GOODS ALMA. So it's exciting data sets, which we can use them to do lots of things. So, and one important feature for ALMACAL is that we don't cover only 1 or 2 bands. The whole ALMACAL database is actually cover the whole ALMA bands. So we could actually have a multi-band data available comparing to the existing blind survey. And so what kind of science we can do with those calibration data? I have categorized them into 2 groups. So the first one is focused on the calibrator itself. So because as I mentioned before, 95% of them are blazars. So we could study them, the light curve, the jets, and the spectral energy distribution. And also since they are quite bright, so they could use as a background source to study the absorptions that's made by the interstellar medium, circumgalactic medium, and the intergalactic medium. And also another way that to use those data is to study the extended fields around the central calibrator. For example, searching for the faint objects, especially the sub-millimeter galaxies, and constrain the number counts. And since all those calibrators actually sharing the same instrument configuration as the science target, so some of those calibrators actually have been observed with very high angular resolution and also very high spectrum resolution. So that makes it possible to also study the morphology and the spectral lines with the object we could find around those calibrators. And in the following, I will most focus on the number counts project. But before I show you the number counts result from ALMACAL, I would like to give you a brief introduction about the background and what we can do with the number counts. So for almost every astronomical object, one important feature we can do is to study its spectral energy distribution. And this is the same for our universe. If you take our universe as a whole, you will find that the energy budget of our universe can be divided into, into three components: the cosmic optical background, the cosmic infrared background, and the cosmic microwave background. And the most well-studied should be the microwave background. It accounts for almost 25% of the total energy budget. And for the rest 5%, it is almost equally shared by the cosmic optical background and the cosmic infrared background. And even though they only account for 5% of the total energy budget, but it actually related to all the processes that's related with star formation, the galaxy formation, evolution, and also the production of the mantles and the dust alongside the universe. So how could we measure the spectral shape for the background emissions? So there are actually two methods. So the first one is from the direct measurements, considering that you have satellites that don't have any resolving power, you actually observe the background. But you need very accurate modeling for the interplanetary dust of our solar system and also the foreground emission from Milky Way. And at the same time, you could also measure a number counts of galaxies. So basically, you just need to integrate all the emissions from every single galaxy. Then you could reconstruct the background. And a more interesting, intriguing thing is by comparing the measurements of the two methods, because it can tell you what's the contribution of a specific population of galaxies to the total energy budget of the background. So especially with ALMA, we could observe the far to millimeter to millimeter band. And in this band is also particularly important. It's mainly because of the so-called negative K correction. So here I showed the typical SED of starburst galaxy that had been put into different redshift. So you'll find that at the submillimeter and millimeter band, we would actually have similar flux densities for the galaxies at different redshift. So that means that submillimeter could be a very efficient way to find those high Z starburst and massive galaxies. And that makes also the number counts of the millimeter galaxies quite sensitive to the galaxy formation and evolution models. And this is what the background what we need the number counts. And here comes to the number counts of the ALMACAL. So because as I mentioned before, the ALMACAL covers all the ALMA bands. And so that makes it possible for us to derive the number counts for all the ALMA bands. And besides, so basically number counts is the number density as a function of the flux density. You don't have any distant or redshift information. Besides the data points, I also showed you some model predictions from, for example, Claudia Lagos and Gregor Poppy, where those semi-analytical or semi-empirical models actually made a quite well predictions for number counts. But at the same time, there is another a group or method that trying to do the post-processing modeling based on the cosmological hydrodynamic simulations. And for this kind of model, actually, it's still struggling to reproduce number counts of submillimeter galaxies. So the multi-band number counts we have present here could be another test bed for the future galaxy formation and evolutional models. And if we go further, here I showed you the differential number counts in two well-studied wavelengths, the 1.2 millimeter and the 817 micrometer. And so there are already lots of works have been done in these two wavelengths. And so first you can see that comparing with the existing data, the number counts from the ALMACAL can consistent with them quite well. And in some bands, for example, band 7, the ALMACAL already stands for the most deepest survey available. And since we have got the number counts and we have made a joint fitting for those number counts, and actually by multiplying the joint fitting of the different number counts with the flux density, we could actually reconstruct the resolved cosmic infrared background. And that is why we come to the final result of our work. So basically, our data points are shown with this Seiyan square with upper row. So it has two parts. The first bottom part is the square is actually the resolved fraction that we only integrated the number counts that have been covered by the existing surveys. So, but we know that every telescope has its limitations. We cannot detect the very faint object below the detection threshold for the telescope. So since we already have the best fitting function, we can extrapolate the best fitting differential number counts to a much lower flux density to recover that the faint object that below the detection threshold. And we found that after we include those faint objects, the result fraction can go up to around 80%, comparing with the best fitting of the direct measurement from
3 minutes.
the FIRAS. Yeah, and so this also told us that those kind of dusty star-forming galaxies should be the main contributor to the cosmic infrared background in the submillimeter and the millimeter range. But should be noted that, as you already can see from the spectrum from the FIRAS, the sensitivity at the longer wavelengths is already not so good. So in order to make a better comparison between the two, to constrain that the different populations contributing to the total cosmic infrared background, we actually need more accurate direct measurement. And yeah, so that is the final results, which lead to me the final summary. So basically, hope I have convinced you that ALMACAL is a very promising survey, which could be an alternative or deep survey for the future, for our future. And also the number counts, the multi-band number counts could be a powerful benchmark for the galaxy formation evolutional models. And finally, by integrating all the resolved submillimeter galaxy found by ALMA, we could find that dusty star-forming galaxies dominate the cosmic infrared background in the submillimeter and the millimeter range. Okay, so I will stop here and would like to take any questions if you have.
Thank you so much for the excellent talk. This is a really great survey that ALMA has, so it would be great to hear if people have any questions or comments about this. Feel free to add the questions in the chat here. Until the questions come in, can I ask you about so you did not talk too much about this in the talk, but about the blazars. What can you learn from the long and deep monitoring of the blazars with the ALMACAL that you often do not learn or learn differently from what you see in lower frequency radio observations of blazars? Do you know if you can elaborate on that?
Yeah, so I don't actually do too much work about the blazar. But I do know that by combining the multiband information from the blazar, for example, here's another plot. It's So for example, here is the jet actually we could find from the different bands, and those this could be contribute to the constraint to help to constrain the SED for those blazars. And there is another work that based on this target has been constrained to trying to distinguish what's the mechanism behind those jets. It's hadron processes or prone process. I'm not so sure. I'm not so familiar with this field, but yes, definitely there's many works that can be do with those data sets.
Thank you so much. Katarina, are there any questions coming in the chat?
Yes, there is. There is a question about if you have any information about the redshifts of the dusty star-forming galaxies.
No, at the moment, most of them, we don't have the spectral information. We have tried to search some of the bright one to see whether they could have been covered by those observations by chance, but we actually don't find many of them. So if you want observation, maybe we need to propose some targeted observation. But at least one thing we could do at the moment is that combining with a photometry with the other wavelengths, we could potentially constrain the photosay of this target. So that's, I think, could be the first step we do to constrain their redshift.
Yeah, there's another comment in the chat that says it's very impressive to see how much you can be doing using normal calibrators. Basically, the side product of other programs. Yeah. Regarding the possibility of lines observed towards the calibrators, you referred to some works. I would like to know if these works within ALMACAL focus on some specific species, or if you try to detect any kind of molecular lines, either in emission or absorption.
Yes, there is another ongoing project. Maybe it should be another PhD student who should focus on it, is trying to blindly search for the emission in all the ALMA fields. So at the moment, we just blindly searching for the dust continue emission. And at the same time, we could also do the blind searching for the emission lines.
Okay. And there's another question. The comment says it is wonderful to be able to use the calibrator data to do top science. Is there a dynamical range limit of combining data from the same target, and will you continue over ALMA lifetime? Yes,
this is quite an important question, because sometimes maybe you could already see something in this plot. Is in sometimes you could find there's something residue in the center of the calibrator. This is because the non-ideal removing for the central calibrator, because we know those blazars, some of them have jet and some of them could be marginally resolved at very high angular resolution. So if we just remove them by a point source, there could be some residue, and those residue can stop you from go deeper if we have more and more data. So if we want to go deeper, we need to find a way that to model those calibrators more better to go deeper. So, but there are have some fields that the calibrator can be removed quite well. For example, on the center of another fields, and for those fields, we could, if we have more data, we could actually potentially push the dynamic range. At the moment, for single observation, the dynamic range of the ALMA could already exceed 1,000. And we have seen that some of those observations, the dynamic range could exceed maybe 10,000. So yeah, it's definitely a promising way to go deeper.
Excellent. Thank you so much for the talk and the answers to excellent questions.